Understanding the derivative of a natural logarithm opens the gateway to a new technique of differentiation called logarithmic differentiation. This technique is related to implicit differentiation. So we're going to take one example and we're going to review the process of implicit differentiation as a warm-up to this new process of logarithmic differentiation. For example, find the derivative of y with respect to x if natural log of xy plus 5x equals 30. Now, the reason we apply implicit differentiation is because we're dealing with an implicit function. An implicit function contains both x's and y's mixed up together, potentially on both sides of the equation. Whereas an explicit function has y isolated on one side and a clear function of x, or an expression involving x alone, on the other side. So we're going to differentiate both sides of this equation with respect to x, and I'm going to indicate that with my differential operator. So I'm going to differentiate both sides with respect to the independent variable x. So the variable in the denominator of my differential operator tells me x is independent, y is dependent. So I'm going to differentiate that first term, natural log of xy, in the ordinary way. And that is, we're going to take the argument of the logarithm and we're going to put it in the denominator, but we're going to put the derivative of that argument in the numerator. Now, because we're dealing with the product of two functions, we're going to need the product rule. Now, with implicit differentiation, we are assuming that y represents a function of x. So remember, when we differentiate y, we're going to have an extra derivative coming out of the chain rule. So looking at the derivative of the product x times y, we have the first function x times the derivative of the second function. The derivative of y is just 1, but because it is an implicit function of x, we're going to multiply by its derivative, dy over dx, plus the derivative of the first factor, that is the derivative of x is 1, times the second function as is. So there we took the argument of the logarithm and put it in the denominator. The derivative of the argument is in the numerator. That required the product rule, also the chain rule there in the midst. Okay, that takes care of the first term. The second term is easy to differentiate because it's a function of x alone, and we have derivative of a constant on the right side, which is just 0. Now that we have carried out the derivatives, we need to do some algebra. That is, we need to solve for dy over dx. That's the derivative that we are seeking. So let's subtract 5 from both sides. And by the way, if you prefer, you can write that dy over dx as a y prime. If you learned it that way, that's fine. We're going to subtract 5 from both sides. We're going to multiply both sides by xy. We can subtract y from both sides. Remember, our goal here is to isolate dy over dx. And then finally, we can divide both sides by x. And let's simplify as we go. I'm going to factor out a negative y from the numerator here and divide by x. So notice we started out with an implicit function, or an implicit equation, and we ended up with an implicit derivative. That is, our derivative is in terms of both independent variable x and dependent variable y. If we start with an explicit function, the derivative is also explicit. That is, a function of x has a derivative that is also a clear function of x. Now, you may have thought of implicit differentiation as sort of a drudgery type complicated problem from Calculus 1, but if you stick with it and you hang in there and you go sign up for Calculus 3, I'll show you a shortcut to that, but not until then, okay? So you'll get a shortcut for that when you take Calculus 3. Okay. Let's take this process of implicit differentiation and learn a new related technique called logarithmic differentiation. Note, logarithmic differentiation can be used to simplify the differentiation of complicated rational functions and functions which have a variable base and variable exponent. Here's the procedure. We're going to take the natural logarithm of both sides of the original function. Then we're going to take advantage of logarithmic properties to expand the expression, and then we'll find the derivative of y with respect to x using implicit differentiation. So in example 5, notice that we're finding the derivative of y with respect to x for an explicit function. Y is isolated and it's equal to a function of x alone on the other side. So this is an explicit function. However, to find the derivative, I would have to apply the quotient rule. Not impossible, but again, it takes a little bit of effort. So we're going to sidestep that effort and do this new process of logarithmic differentiation. So number 1, we're going to take the natural logarithm of both sides of the original equation. So this is going to look like natural log of the left side y equals natural log of the right side x squared divided by the square root of x minus 1. Now, I'm going to use my log properties to expand the right side. So we can take natural log of the numerator minus natural log of the denominator. Both of those logs have an exponent, which we could move to the left. We can rewrite this 2 natural log of x, remembering that the square root is a 1/2 exponent in disguise. We can rewrite that as a 1/2 coefficient natural log of x minus 1. Make sure you are very clear that the exponents that we moved there were under the authority of the power rule for logarithms. That is, if your argument has an exponent, you can move it down in front as a coefficient. Although it feels like the power rule for differentiation, we were not differentiating on that step. But after we've expanded, we are now ready to find the derivative with respect to x using implicit differentiation. So I'm going to go ahead and write out my plan. My plan is to find the derivative with respect to x of the left and right sides. Also, this would be a convenient time to point out the different types of notation that I'm using. In one case, we have d over dx. In another case, we have dy over dx. There's a little bit of a difference. In the case of dy over dx, this is what we call Leibniz notation, named for the mathematician that pioneered this notation. Leibniz wrote dy over dx as an expression which represents the derivative, whereas the d over dx over here is called the differential operator. Let me be specific. It's the differential operator. So it is applied to a function. It's a pending operation. It's saying go find the derivative of whatever is inside brackets. Whereas the dy over dx is equivalent to the derivative. It can be used to substitute in place of the derivative. So again, just a little subtle difference to point out there. Let's go ahead and carry out the calculus. Now on the left side, we're finding the derivative with respect to x of natural log of y. Notice the mismatch in the variables. The variable of differentiation is x, whereas the variable in the argument here is y. The variable in the denominator of the differential operator identifies the independent variable. No big deal here. We're used to x being independent, but in case you had different variables, you'd be able to identify that. So when I differentiate natural log of y, I'm going to differentiate it like I normally would. That is, I'm going to put the argument in the denominator. But then, because y is a function of x, we're going to have to multiply by its derivative with respect to x. That's the chain rule part. Okay, on the right side, we're dealing with functions of x alone, so no worries about the chain rule. The derivative of 2 times natural log of x is 2 times 1 over x. And for natural log of x minus 1, we have constant coefficient 1/2. Argument goes in the denominator, derivative of the argument in the numerator. So we do have a bit of an implicit equation here, but it's going to be very easy to solve for dy over dx. I'm actually going to take one step to clean this up. I'm going to write this as 2 over x minus 2, oops, that 2 goes in the bottom, doesn't it? 1 over 2 times x minus 1. And I said one step, let's take 2 steps. Let's go ahead and get a common denominator, which in this case would be 2x times x minus 1. As we update our numerators here from this old denominator to this new denominator, we have gained the factor of 2 and x minus 1. So I'm going to multiply 2 both by 2 and x minus 1. And from this old denominator to this new denominator, we've gained a factor of x. So I'm going to multiply the original numerator 1 by x as well. Okay, simplifying that, we have 4x minus 4 minus x. I'm going to leave the denominator factored. That's a good practice. And simplify our numerator. And then we'll be back on track. Looks like we have 3x minus 4 over 2x times x minus 1. So what were we doing after we got lost in all this algebra? Oh yeah, we were trying to find dy over dx. There it is. I found it right there. All we have to do is solve for it. And that's a piece of cake. We just multiply both sides by y, and we end up with y times 3x minus 4 over 2x times x minus 1. Now, there's one little issue here. If you'll go back to our original problem, we started with an explicit function. That means I should be able to obtain an explicit derivative. And at this point, I have an implicit derivative. That is, I have both x and y involved in the derivative. So we're going to remedy this by replacing y with its equivalent in terms of x. From our original function, we can see what y is in terms of x. So I'm going to take the x squared over the square root of x minus 1 and plug it in over here for y. And then looks like we'll have a little more algebra to do. So we have dy over dx equals, now I'm replacing y with its original expression in x, that was x squared over the square root of x minus 1 times 3x minus 4 over 2x times x minus 1. So notice one of these x's will cancel that exponent there, and we have x minus 1 to the 1/2 power times x minus 1 to the 1st power. When multiplying like bases, we can add those exponents. So this is going to give us dy over dx equals x times 3x minus 4 times 2, or divided by 2 times x minus 1. 1 plus 1/2 gives me 3/2 power. So the algebra was pretty involved. Compare that maybe to the algebra of applying the quotient rule originally. Either way you differentiate, either directly with the quotient rule or indirectly using this new technique of logarithmic differentiation, you should end up with a unique derivative. So logarithmic differentiation is an option to differentiate complicated fractions or complicated rational functions. However, it is a requirement when we have the case of a variable base and a variable exponent, as example number 6 will show. We want to find the derivative with respect to of y with respect to x for y equals sine of x to the tangent of x. I cannot apply the ordinary power rule for differentiation here because I have a variable here and a variable here. If we have a constant in the exponent, we can apply the power rule for differentiation. So in this case, logarithmic differentiation is required. So remember, we're going to start with some algebra. We're going to take the natural log of both sides. The presence of that natural log allows me to apply a logarithmic property, which says I can move the exponent of an argument down in front as a coefficient, so that we obtain tangent of x times natural log of sine of x. So we are using the logarithm to break apart the exponent from its base. We've moved it down in front as a coefficient. Now we can differentiate both sides with respect to x. Now, when working with logarithmic differentiation, you're going to observe a pattern. The left side always looks the same. It's always going to be 1 over y dy over dx. Now, on the right side here, notice I've got a lot going on. I've got the combination of the product of two functions of x and a composition of two functions of x. So my product rule is what I begin with. We'll take our first function, tangent of x, times the derivative of the second function. Now the second function is the composition. It's a natural log. So we're going to take the argument of the natural log in the denominator and the derivative of that argument in the numerator, plus the derivative of the first function. Remember, the derivative of tangent of x is secant squared of x, times the second function, as is natural log of sine of x. Now, let's see if we can simplify a little bit before we isolate that dy over dx. Now, think about tangent. Tangent of x is sine of x over cosine of x. If I write it like that, then I can see here this first product is a fancy way of writing 1, which is much simpler than what we had originally. So we're going to cancel our common factors. That's going to make a 1, and we'll multiply both sides by y in order to isolate our derivative. So we end up with dy over dx equals y times 1 plus secant squared of x natural log of sine of x. Again, we started with an explicit function. We should anticipate an explicit derivative, that is in terms of x only, but we do have it in terms of x and y. This is going to be an easy remedy. We're simply going to replace y with what it is originally defined as in terms of x. So y will be replaced with sine of x to the exponent tangent of x times this other factor. I believe that's as good as that one is going to get. I don't think there's anything else we can do to simplify, so there is our explicit derivative. So again, logarithmic differentiation can be used to break apart complicated functions that look like fractions. It is required for the situation where you have a variable base and a variable exponent. So we're going to continue practicing this technique on the next two examples. Now, for example 7, think about what direct differentiation would require. Of course, we're going to have to do the quotient rule, but entangled in that quotient rule, we're also going to have to apply the chain rule with these powers of functions in both the numerator and the denominator. So that just indicates quite a bit of algebra. So to sidestep that approach, not impossible, but a little bit tedious, we're going to instead do a convenient logarithmic differentiation. So remember, this begins by taking the natural log of both sides of the equation. We have to apply the natural log to both sides as a basic rule of algebra. Then we can expand the expression using log properties. So we're going to begin by taking logarithm of the numerator minus natural log of the denominator, and then, not by calculus but by algebra, we can move the exponent of the argument down in front as a coefficient. Then we're ready for some calculus. So I'm going to indicate that I'm preparing to differentiate, and I'm also going to identify the variable of differentiation using my differential operator. Now don't skip that step. It's an easy one to skip, but it is essential as far as explaining your process or presenting your process. Part of this class is not just getting the right answer, but demonstrating correct logic and reasoning through your steps. Now we're ready to execute the differentiation. The left side is familiar. Once again, we have 1 over y times dy over dx. Look how easy it is now to differentiate the right side. We have coefficient 8 times the derivative of a natural log that contains argument in the denominator, derivative of the argument in the numerator, and the same pattern for our second logarithm here. I'm going to clean this up and obtain a common denominator, which is the product of our two distinct denominators. Notice our original numerator is 8 times 3, or 24. It's going to need to be multiplied by 2x squared minus 1. Second factor here is 16x. It gains the new factor of 3x plus 5. Okay, let's simplify that numerator. To obtain 48x squared minus 24 minus 48x squared, that's convenient, minus 80 over this same denominator. So we have 1 over y dy over dx equals negative 104 over our denominator. And the last step is to multiply both sides by y so that we can isolate dy over dx, the derivative that we're after. So we can have 104y, which is the implicit form of our derivative, but because we started with an explicit function, we want to end with an explicit derivative. So we're going to replace y with its original expression in terms of x. So I'm going to write this as negative 104 over 3x plus 5 times 2x squared minus 1 times the original y function, 3x plus 5 to the 8th over 2x squared minus 1 to the 4th. We can cancel a little bit here. One of the 3x plus 5s will cancel to make that an exponent of 7. We can combine powers of 2x squared minus 1 in the denominator. And we will obtain dy over dx equals negative 104 times 3x plus 5 to the 7th divided by 2x squared minus 1 to the 5th. We would have arrived at this same destination had we applied the quotient rule to the original function. The algebra may have been a little more challenging. Okay, one last problem. Notice on example 8, we have a variable base and a variable exponent. This is the case where logarithmic differentiation is not an option. It is a requirement in order to separate the variable exponent from the variable base. Once we have taken the natural log of both sides, by properties of logarithms, we can then move the exponent down as a coefficient. So our coefficient becomes natural log of x, leaving behind natural log of x. So this one's kind of interesting. Notice we have natural log of x times natural log of x over here on the right side. That's equivalent to natural log squared of x. Now we are ready to differentiate both sides with respect to x, and I'm going to indicate that with my differential operator. Remember, don't skip that step. So we have planned our differentiation. Now we're ready to execute it. The left side, as usual, is the familiar 1 over y dy over dx. On the right side, we're going to start with the chain rule, start with the power rule. So we bring the exponent down in front as a coefficient. Now this is the calculus power rule, not the logarithmic power rule. So we have 2 down in front, the base stays the same, and then we decrease the exponent by 1, which just gives me a 1, no need to write that. And then the chain rule says multiply by the derivative of the base, which is 1 over x. We finish, as always, isolating the derivative of y with respect to x by multiplying both sides by y. So I'm going to rewrite this 2y over x natural log of x. Y from the original function is x to the natural log of x. So the derivative of y with respect to x is 2x exponent natural log of x. I'm going to bring the natural log of x up to the numerator over x. Now that's not too bad, but do notice that we have a power of x in the top and a power of x in the bottom. So we could combine those powers. Remember, when you divide like bases, you subtract the exponents. So we could say natural log of x minus 1 times natural log of x. We just took the exponent here and subtracted the exponent here and made it a concise, efficient, explicit derivative. So the thing to remember about logarithmic differentiation is it is an option for simplifying complicated rational functions or functions that look like fractions by separating them with log properties before applying implicit differentiation. But logarithmic differentiation is required if you have the pattern of a function that has a variable base and a variable exponent.